Hello, everyone. Good morning, good afternoon, or good evening, depending on where you are joining us. My name is Maria Eugenia Escobar, and I am the current president of the Brazilian Soil Science Society. It is a great pleasure to welcome all of you to this joint Brazilian Soil Science Society and the Soil Science Society of America webinar. Today, we are hosting the third event collaborative organized by our two societies, a partnership that has grown stronger over the past 2 years and continues to foster meaningful opportunities for scientific exchange. This webinar is also part of our celebration of the World Soil Day, which will be observed on December 5th, this Friday. This year's fall campaign theme, Healthy Soils for Healthy Cities, reminds us of the essential role that soils play in sustaining life, resilience, and well-being in urban environments. In alignment with this global message, our theme today is restoration strategies that promote healthy soils. On behalf of the Brazilian Society, I would like to sincerely thank our invited speakers for kindly accepting this invitation and for sharing their valuable knowledge with us. As in our previous joint webinars, we are pleased to have one speaker from each society. It is now my pleasure to introduce our co-moderator, Dr. John Kavar, President-elect of the Soil Science Society of America, and also part of the member committee. Please, John, the floor is yours.
Thank you, Maria. Yes, welcome everyone from the Soil Science Society of America. I will officially be the president-elect in January, so I'm not quite there, but I'm learning the ropes. I thank the Soil Science Society of Brazil for hosting this webinar, and I look forward to future collaborations. Again, this is the third in our series. There will be more coming. We are trying to collaborate long-term, so the two societies hopefully will form a long-term relationship. Right now, it's possible to have joint memberships between these two societies. And so that's a very good thing. That just happened in the recent past. In the future, we will have symposia at each of the meetings, the annual meetings. And so the collaboration will be long-term, I hope. So with that, I will introduce our first speaker. He is Dr. Tom DeSutter. I have a few points here that I can, a few background information for Tom. He received a PhD in 2004 from Kansas State University in Manhattan, Kansas. He completed a postdoc with the USDA ARS here in Ames, Iowa. And so he was working in the same lab where I am currently working. So that was in 2006. He was then hired as a environmental soil scientist by the School of Natural Resources at North Dakota State University in Fargo, North Dakota. His primary research interests are saline and sodic soils, reclamation of energy extraction impacted soils, and instrumentation for measuring soil parameters. Dr. DeSutter has taught introductory soil science, soil and land use, and environmental field instrumentation and sampling, and also soil genesis and surveys. So quite a broad range of topics there. An interesting personal note is he is the co-author of a book entitled Catfishing on the Red River of the North. So from that, you can gain some insight into one of his hobbies. So without further ado, Dr. DeSutter, the floor is yours.
All right, John. Well, thank you very much, and great to see you out of Ames, Iowa there. So my name is Tom DeSutter. I'm a faculty member here at North Dakota State University. I'm been here about 19 years, and so have a few years under my belt anyway. Let's see if we can get this to work. And so one of the things that I've focused on as of recent is more on the reclamation side. And so my background in environmental soil chemistry, my instrumentation interest, it all kinds of leads to, and most of the problems that we have that we deal with are some sort of reclamation, whether it's compaction or lack of water in the soil or so on and so forth. But so today we'll talk about this, and I want to make sure that we understand that simple is in quotes. It's not simple, and we'll kind of walk through some of that. So I'm going to provide some context of our location, where we spend most of our time, just so you can kind of get a sense of why we're doing the work we're doing. So I'm currently in Fargo, North Dakota, and which is, if you can see my mouse, it's over in this side of the state. The area that we're going to be focused on is on the western side of North Dakota. And then you can see there's Saskatoon, there's Winnipeg, very, very close to us. And so we have some really good collaborators from the University of Manitoba. And so, but the area that we're talking about is the Williston area. And part of the challenge in reclamation is always water. And so I always joke, I'm originally from the state of Iowa. And the joke is, and sort of a ha-ha, is if we got the amount of water that Iowa got, we wouldn't have near the issues with reclamation that we do. Because they get kind of in that 30 to 40 inches of rain per rainfall per year. But if you can see on ours, it's generally in that 12 to 14 inches or 20 to 40 centimeters per year. And so whenever you think about rainfall, you need to also think about the potential evapotranspiration. And so you can see that we have about 5 times more PET than we do rainfall, which is very challenging from a reclamation standpoint. And so in this region, you see crops that are grown that are very, sort of drought tolerant. We have hard red spring wheat, which makes up 85% of the wheat, and Durham wheat makes up the remaining. Canola, forage, some soybeans, but dry edible beans. So those are kind of the context of the area that we're working on with respect to the agriculture. Many of these soils are glaciated north of the Missouri River, and south of the Missouri River, they're probably in that millions of year old sort of non-glaciated region. And so we're going to focus today a little bit on the area of the Bakken Shale Formation of North Dakota, so which resides in the what we call the Williston Basin. And so we've extracted over 5 billion barrels of oil from North Dakota, and all this oil comes from these 4 formations: the Three Forks, the Lower Bakken, the Middle Bakken, and the Upper Bakken. And so these are where our we only have like 900,000 people in the state, but we have oil and gas and agriculture account for about $70 billion in our economic prosperity. So you have to talk about both of them at the same time. And so all of this shale oil is basically extracted from those formations using what we call hydraulic fracking. And so to do that, wells are drilled, and these sand-sized particles, or not sand-sized, or they're sand, are about 100 micron in size. And so this is about 100 micron is about the width of a human hair. Not my hair. I've had way too much erosion. But John Kovar's hair, as an example, that's the thickness. So we're talking about very high pressures, adding this sand to bust up the shale, which allows then the oil and the oil to flow to the wellhead. And so on a daily basis, there's about 1.2 million barrels of oil, which puts us at number 3 in the nation, in the United States, in oil production. But we also have a lot of natural gas, about 3.3 to 3.5 billion cubic feet of natural gas per day. And in these shale formations, because these systems developed under oceanic pressures, we get about equally amount of produced water, which is basically salt water, as we do oil. And so that ratio changes, but for the most part, just think of it as a 1-to-1 at this point. And so those are the types of things that, the oil is something that we want, the natural gas is something we want, the produced water is something that we have to deal with. And so this produced water is about 5 times more saline than seawater. And so as it gets onto the landscape, it can cause some fairly significant changes and damages to those soils. Some of the oil that we produce gets refined in the state, and a lot of the natural gas, we have a lot of natural gas pressure stations and plants. They handle a lot of the natural gas that then gets exported out of the state. And so to kind of give you a visual of that region, you can see the Williston Basin kind of in the darker color, and the Bakken Three Forks in the lighter color. Each of those colors represent its well pad density per 20 square miles, and those are the count of points. So the darker the color, the more well pads there are in a 20 square mile area. And so where these are mostly highly concentrated are where that Bakken formation is most thick. And so that's where they're extracting the most oil. So you can see on the left-hand side, you can see Williston, and on the right-hand side towards the corner, you can see Fargo, which is where I'm located. And that's about a 6-hour drive for most of our work out in the western part of the state. And so about 80% of the oil in North Dakota leaves through pipelines. So here's an example of a pipeline, which is actually a water pipeline, but the context is the same. These are areas where they scrape away the topsoil, and when they dig the trench, they will have they separate the topsoil from the subsoil. And then after the pipe has been laid, then they'll work backwards and lay that soil back down. But we have about 30,000 miles of pipeline in the state. And if you can do the math, but it's about 100 feet of right of way, and you can take that times 30,000, and you can calculate the amount of disturbed soils fairly quickly. And so something to think about, even in the transport phase of oil and gas, there can be a bit of soil disturbances due to that. And so when you start moving product around, you do have the possibilities of accidental releases. And so North Dakota has about 1 reported release per day, not to the magnitude that gets these sort of headlines. A lot of them are 10 barrels, and a barrel is 42 gallons. So a lot of them are very, very small, and they're easy for the responsible parties to take care of. It's these larger ones that get the headlines, and that's where sometimes we get brought in to help with some of the research questions, or the cleanup, or the impacts of how those might happen. And so this is an example of a produced water spill that was probably 20 to 30 years old, that never really got cleaned up. It's easy to see. You have high concentration of salts that's pretty much devoid any vegetation. Fortunately, this is not necessarily something that's widespread in our current oil boom. We have companies who are responsible, that do a very good job of managing their accidental releases. One of the releases that we're going to talk a little bit about is this spill that occurred in the northwest part of North Dakota. You can see the inset there. This was about 20,000 barrels of crude that basically leaked through a hole that was about the size of your thumb. Probably, maybe an estimate of a month or more, but it ended up impacting a fair acreages of soil. Here, this about 7 acres, but through the cleanup process and the safe wall that I'll show you, it ended up being about 77 acres that was disturbed. And so one of the things, there's a red X on your screen. Just kind of keep that in mind, that's kind of a reference point for the rest of the talk. So the soils that were impacted, and it ended up being over 1 million tons, US tons of soil that went through a process called thermal desorption. And so this was a process basically to remove the hydrocarbons from these soils. And then the soils that were then at the end, you can see the front end loader in the lower right hand corner here. This is now what we consider to be clean, less than 500 or less than 1,000 parts per million total petroleum hydrocarbons. And so this operation ran for a few years. Here's an example a few years later. You can still see the X over here, the impact that it had. A lot of because this was a glaciated region, there's lots of areas of sand and gravel lenses, and under high pressure, the oil found those sand lenses and moved fairly quickly and spatially. And so they ended up having to dig down about 60 feet to remove the impacted soil. The impacted soils were then put on an area where it was continually turned to basically reduce the concentration of hydrocarbons over time, which then allowed the thermal desorption unit to work more efficiently. And so we're going to talk about this area over here now, which is on the top of the screen, and those will be our plots that we will discuss. And so we were able to get plots that were built. These are plots that we had. This is the stockpile soil. That was that soil that had about 1,000, 1,500, 2,000 parts per million of total petroleum hydrocarbon. This is the post-thermal desorption soil. And then we had topsoil that was never impacted. And so these were the bases for our treatments that you can see on the right-hand side. You can see them mostly by the colors. So the stockpile soil was subsoil. And most of the soil that was treated at this site was subsoil. The topsoil was stripped off that was not impacted, but most of it was the subsoil. But we wanted to see, can we actually mix the soils in a way on a one-to-one basis to see whether or not we could create our own soil, in essence, creating our own Technosol, if you will. And so that was one of the primary goals of this research, was to focus on, can we blend soils and get the same yield as we would if we just had a unimpacted topsoil. And so our cropping systems were in 2016, 17, and 18 were hard red spring wheat, field peas, and then hard red spring wheat again, which is a common rotation for this area. So we're going to go right into the data. So again, we have topsoil that is dictated by A. We had thermally desorbed plus our topsoil on a one-to-one mass. In our stockpile soil, again, which had hydrocarbon in it, but it was all subsoil. And then we had our thermally desorbed soil, and then our stockpile soil. So if we just look at the top graph here, the 2016 wheat, anything that had a horizon in it, there was no yield differences. And that didn't matter if it was 2016, 2017, or 2018. And so that told us that in an area that gets a very limited amount of precipitation, that using unimpacted topsoil blended with a subsoil, you can achieve the same yields than if you had 100% topsoil. So it really points towards that, man, you really got to take care of that topsoil. It is the goal that our farmers and ranchers have, and their livelihood depends on it. And so that was one of the things that we were really excited about to see. Not that we don't want to use 100% topsoil, but if it's not available, can we still use a blend? And so it's easy to see, though, when you look at the organic carbon, we have our yield over here, we have our soil organic carbon over here. It's easy to see when you have your thermally desorb, and then your mixes. Here's the A, here's our yield, and here's this is 2.5% soil organic carbon in our blends, which are one-to-one blends. They basically showed what they showed, right? They're right in that pocket between the no organic matter or no topsoil at all and 100% topsoil. And so organic matter is important, and there will never be a time where we do not discuss and do not promote conservation of soil organic carbon. And so then in 2019, we were a little bit more interested in now the biology of what was going on. So we planted sorghum in our plots. And this is Steve Jensen. This is that big X. After everything was done, all the rocks that were in that hole ended up on this big pile. And so we call this pile Mount Patty because the one thing she wanted was that rock pile removed, and unfortunately it's still there for her to see. So let's start with the biodiversity. One of my students, Zach, he was looking at colonization of arbuscular mycorrhizal fungi. And so we have our treatments here again. Again, our blends, our one-to-one blends are the plus A's, thermal desorption or the stockpile. But if you look, you would expect, oh, that's the most vibrant, right? That's the most, but actually the soils that were the most degraded, the stockpile, had the greatest colonization of arbuscular mycorrhizal fungi after 4 years. And so what does that tell us? Well, it tells us that our systems want to move towards the mean, right? They will recover over time, but it takes time. And when you are in limited rainfall environments, mixing the soil one-to-one can be a good option for better colonization of our soils, especially the ones that are the most disturbed. So then Zach looked at phospholipid fatty acid analysis, which gives you a little bit maybe a holistic look. You can see with the blends again, here's our unimpacted A, here's a blend with the thermal absorption with the stockpile. No statistical differences between those, right? So it does point again towards the fact that we can recover soils even if we are limited a little bit. Now, one of the things we'd like to do is maybe do that more on a percent basis, so 25% or a 2-to-1, 1-to-1, 1-to-2 sort of basis, and see what we can sort of like get away with. Here's some of the references for these. You can find these later. So then, part of this whole question is like, can we amend soils with stuff, right? There's so many different products that are sold, not only to farmers and ranchers, but also to folks doing reclamation. And so one of the things that we've been looking at a bit are these proganics. It's kind of a blend of biotic soil media. You can buy it and it'll come on a truck kind of thing. But the one thing, when you looked at these thermally desorbed subsoils here in a non-contaminated subsoil, adding the proganics actually did pretty well, looking at just base efflux CO2 concentrations. And in North Dakota, we have about 6 to 8 million acres of saline soils. And so adding the proganics compared to compost, spent lime, and to the control actually did pretty well. Now, the longevity of that is going to probably be an issue, but it does show that some of these products can enhance some of our soil properties. And so the other thing that we've always been interested in are these super absorbent polymers. And so these are materials that can absorb water hundreds, maybe 1,000 times their own mass. They're not terribly expensive, but there's a cost associated with them. And one of the things that we're always interested in, especially these semi-arid environments, is like, can we increase plant available water? And that's always the trick. It's like, how do you conserve water? Because if you have a PET that's 5 times precip, as soon as the sun comes out after a rain, that water wants to move back up into the atmosphere. And so these polymers possibly could be an answer, or at least a recipe in part of that. So my student Megan, and she was co-advised with Aaron Day. She did a pretty large summary of data, and it did point towards that, it can enhance some of these properties. And so she then did a laboratory experiment, and we did a number of soils, soil series, Fargo, Williams down the line. More importantly, look at the right-hand side. You can see I added the colors of where those soils would be on the textural triangle. Happy World Soils Day. And so on the what you can see though is our rates, which correspond to 0, 0.04, 0.08, and 2% superabsorbent polymer as you move down from 0 to 5. You can see that if you look at the 0 and then you look at the highest rate, every one of our soils, which it was a high clay soil, much higher clay soil versus a much sandy loam soil, you did see an increase in plant available water. So that does lend itself a little bit to like, hey, maybe we got something here. Now we need to do more field work on this. It is a hole that we've had, whether or not it actually impacts yield. And so yes, it does it in the laboratory, but does it actually impact in yield? And so here's Megan's paper here. It's really good work, and she was an outstanding student. So then that points us towards like, okay, now what about organic amendments? And we have, we don't have as many people in North Dakota. Iowa has 3 million people. Minnesota has 5 million. North Dakota is like 900,000, right? So we don't have as much of a population. So we don't produce as much biosolid, if you will. We have large communities. So we have one facility in North Dakota that produces Class A biosolids. And so we were interested as like, okay, and it happens to be in Williston, the area that we're working. Can we use these biosolids as an amendment to increase plant available water, nutrient cycling, the whole thing? And so one of the things that we then did, and Aaron, my student, is working on it now, is we're trying to figure out how it affects plant available water. Because again, if it's not going to affect plant available water, just because you add organic matter doesn't mean it's going to increase plant available water. So that was one of the things that we're very always keenly interested in, is conserving water, because we don't have a lot of it. And so Aaron then went through and so basically he's still in the process of running this data for his stats. But one of the things we noticed right away was that it's a bit hydrophobic. And so I think when you're thinking about organic materials, and you're thinking about, oh, how do we increase plant available water? You have to make sure that it's not hydrophobic, because if it takes a year or two to hydrate, what good is it possibly going to do, right? Other than possibly reduce the bulk density. And so here on the figure on the right here, you have gravimetric plant available water. And on the bottom, you have your biosolids treatments where the 1x rate is 6.7 megagrams per hectare, which is this one. So there really wasn't any difference. And he's going to run the stats, and I'm sure there's no difference. But part of it might be that the fact that it is a bit on the hydrophobic side. So the other thing I want to talk about a little bit about is thinking about clay mineralogy. And this is Michael Thompson's. He's smiling ear to ear right now. And so we did a study trying to figure out, like, okay, if we're going to do reclamation, us trying to understand whether or not what clay mineralogy dominates will then dictate how reclamation proceeds. And so we did a saturated hydraulic conductivity study with Josh Heitman and Aziz Amuzagar over at NC State. And so we're looking at this from the standpoint of the open circles are kaolinite, 100% pure kaolinite, and the black circles are montmorillonite. So we have a 2-to-1, we have a 1-to-1 non-shrink swell in the kaolinite, and we have a 2-to-1 shrink swell in the montmorillonite. These are the two sort of like clays that dominates North Dakota a little bit. And so, so if you look at the KSAT and you have the percent clay down here, kaolinite, man, you could add a lot of kaolinite and it didn't change the hydraulic conductivity very much. However, when you added the montmorillonite, it's exactly what you would think, right? And here's a break here, so you can kind of see it gets pretty low, if not almost non-existent. And so in our soils that are glaciated, we have a lot of 2-to-1 smectite montmorillonite clays. Our reclamation mentality is going to be a little bit different than it is if it's a kaolinite or an illite, which is a 2-to-1, but a non-shrink swell. So then we wanted to see, okay, how do our pedal transfer function models model clay, right? And so basically, if you run this into these pedal transfer function models, they mimic pretty much kaolinite, and they pretty much do not get close to an understanding smectite or montmorillonite. And so I think that's another area of improvement for our pedal transfer function models, is the inclusion of clay mineralogy. And there are places now, and we send ours to a lab in Canada, and we can get quantitative mineralogy. It's like 200, $300 a sample, but man, you can learn a lot by just understanding that clay mineralogy. So I encourage everyone now in our studies, don't just put clay. Actually, let's start putting in the mineralogy so we can better understand the results of our studies. Okay, kind of in a synopsis, summary, the two things, again, can't talk about this enough. Alleviation of compaction is going to be an issue. When you have reclamation and disturbed soils, compaction here is going to be an issue. You don't want to be farming 10 centimeters or 15 centimeters of soil when you have a profile of soil. But when you have compaction, and here's an alfalfa root, it comes down and it goes straight to the right. It can't go any further because it's too compacted. And so this happened to be on a pipeline where a lot of the traffic occurs in that work area. The other thing I think is like critically important to understand are our soil forming factors. But so if you kind of look at this is by Les Henry. He was an excellent soil scientist who passed away here a year or so ago. And one of the things in his book, he said, in my fourth year soils course, I often provoked some thinking by listing the soil forming factors as water, 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 and snow. Okay, he's in Saskatchewan. He gets about the same climate as we do. But he's pointing out how important conservation and management of water is, not only for soil forming factors, but also in our case, the growth of plants. We have a very short growing season. It's 5 months, 4 months, somewhere in that really tight timeline. And so we do not want to be water starved in reclamation during that period, because we need that growth to show that reclamation is proceeding, right? And so again, water, 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 maybe a little bit of snow, which we have out here today. Okay, so the holistic approach for remediation, reclamation, or restoration, the beautiful thing about soils, right? You need to understand the physical, the biological, and the chemical properties. And so we covered a few of these here today. At the end of the day, you get at soil function and quality, but at the end of the day, it's about yield and productivity. And so thinking in a three-dimensional sort of way is what we do, and it's what we enjoy. And so, but from a reclamation standpoint, it's imperative that we do that. Okay, so is this a simple thing to do, right? Is reclaiming soil simple? I can tell you right now, it's not as simple as doing AI, right? I did this in about 10 minutes. And I wish soils were this easy where we could just plug into AI and it came out with an answer that was going to work 100% of the time, right? And so I do think it's important that we understand that even with advancements of AI, we still cannot control the weather and the climate. And so we have to use the best tools in our toolbox so that we better understand what is the limitations, was it chemical, physical, or biological, and how we overcome those. So I want to make sure that Dr. Miranda Meehan gets a nod here. Her office is right across the wall here, but she's part of our reclamation group. And as is Aaron, as is Chantel, as Violet, and all the other graduate students that we've had in this program. And so I'll leave it at that, but there are no simple approaches, but we are getting there with our understanding of what are some of the limitations. And it's very regional specific, right? And it's clay mineralogy specific. And what we do during the reclamation process will dictate how many years down the road it takes for those soils to recover. So I'll leave it at that. And I thank you everyone for joining us today, and happy World Soils Day on December 5th.
Thank you very much for this excellent presentation, Tom. We truly appreciate your contribution and the insights you have shared with us today. Well, now it is my pleasure to introduce our second speaker, and I am personally very happy to do so. Professor Tiago Osório Ferreira is a longtime colleague and friend. We have known each other since the early careers of my career here in Brazil, when we were both faculty members at the Federal University of Ceará. It is a great pleasure to welcome him today to join this webinar. Tiago Osório Ferreira holds a degree in agronomic engineering from Federal University of São Carlos, a master and PhD in soil science and plant nutrition from ESALC, University of São Paulo, including a doctoral internship at the University of Santiago de Compostela in Spain. He is an associate professor at the Department of Soil Science at ESALC as well, a CMPQ Research Fellow Level 1C, and Director of Dissemination of Sea Carbon. Currently, he serves as Deputy Coordinator of the Graduate Program in Soil Science and in Soil and Plant Nutrition, and of the Specialization Course in Environmental Management. He acts as editor of national and international scientific journals and has supervised more than 100 students, including undergraduate, masters, PhDs, and postdoctoral researchers. His research focuses on the biogeochemistry of coastal wetland soil, land rehabilitation, and carbon stabilization mechanisms. He coordinates the Soil Geochemistry Research Group, which maintains strong international collaborations with universities in Europe, United States, and Australia. Tiago, the floor is yours.
Thank you, Maria, for the introduction. I will share my screen. Let's see if this will work. I believe you are seeing my slides, am I right? Okay,
yes.
So I would like to start by thanking the invitation. It's a true honor to take part on this partnership between both societies. So my official thanks to the Brazilian Soil Science Society and also for the SSSA. It's a great honor to be invited to this. So before we jump into the topics, which is actually talking about Technosols, I would like to start a little bit, and Maria already helped me with that, talk about a little bit about my background. My background actually is pedology. And as Maria said, I lead a group for the past 15 years, which is dedicated to studying soil geochemistry. So a lot, if not everything that I'm going to show here in my slides, in my presentation, is actually the fruit of work of many talented young scientists. And you can see the name of them in this slide. They are in different stages of their career, but they are incredible young scientists. And so I share my presentation with them. And of course, we have, as Maria also mentioned, some good partnerships going on, collaborations with other universities, not only in Brazil, but also abroad. And many of the data that I'm going to show here is part of those collaborations, okay? So, of course, because of my background, due to my background in pedology, our research group is usually dedicated and also working with soil geochemistry. Our research group is usually dedicated in understanding the geochemical mechanisms behind the soil forming processes. And this is an approach that I'm going to use in our presentation here. And it is usually the approach that we use in all of our research. And I really enjoy this type of approach. And I usually use this slide that I'm showing you guys here now, that it is nice to think about the soil forming processes. When you get to understand the mechanisms, the geochemical mechanisms behind each of those processes, you sort of get the functioning of the soil. So each process functions as the gear inside each soil for us to understand their functioning, but also to understand the linkage between soil forming processes and the ability of the soils to deliver different soil functions, such as provision of foods, nutrient cycling, and so on, and also ecosystem services. So behind all this, there is always soil forming process and understanding the geochemistry behind it. Today, we are going to talk about the one function, carbon storage, and of course, about Technosols. So this is going to be sort of my approach for here, from here to the end of the presentation. So let's start with Technosols. What are Technosols? Professor Thomas DeSutter mentioned the Technosols in his presentation. So Technosols actually is a reference soil group from the WRB. It was recognized by WRB in the year of 2006, and it's defined as soils containing significant amounts of artifacts which are actually produced by human activity. So we have natural soils that are formed from rocks, from sediments, but when we talk about Technosols, we are dealing with soils that can form from materials that were produced by human activity, such as solid waste coming from different, for example, from mining or from any industrial activity. The Technosols have, of course, to satisfy some rules. And for example, it has to have more than 20% of artifacts of that nature inside the first 1 meter of soil, okay? But what I would like to stress today and highlight today is the fact that we can have two types of Technosols. Those that are produced unintentionally by human activity, and those that are produced intentionally by human activity. So today I'm going to show some examples of both cases, but more importantly, my idea is for us to see what we can teach about soil forming process from Technosols, and what we can learn, what the Technosols can teach us, what we can learn about soil forming process, but also what we can learn also about their ability to provide soil functions and sustain ecosystem services. Okay, so let's start with a very important case that happened in Brazil with non-intentional Technosols that were formed actually because of the largest and the worst mining disaster that took place in Brazil, Mariana mining dam collapse. This work was performed by these two brilliant scientists, Dr. Hermano and Dr. Amanda, Dr. Amanda and Dr. Hermano. And what we did in this work was, after this huge mine collapse that we had in Brazil, the iron mine tailings that were inside that dam, they reached this estuarine environment in the coast of southeast of Brazil. So basically, what we are looking at this picture is a few days after the dam collapse, and we can see the red color going to the ocean. It's basically iron oxides that came from inside the iron mine tailings. Zooming a little bit in, we can see in the left a very clear site with sandy, flaky, sandy islands, very common in this estuarine parts. Those sandy islands, fluvial islands, usually didn't show any type of vegetation before the disaster, but some years after the disaster, we can see a lot of vegetation colonizing those islands. And this is something that was very characteristic of the years after the dam collapse. And if we look a little bit closer, a little bit more zoom, what we are looking in this picture is a very thin layer of iron mine tailings, basically composed of highly crystalline iron oxides that in a few years passed to be a very thick and a very thick accumulation of iron mine tailings and very colonized by plants with a very dense colonization by plants. And what we saw in our studies is that after a few years, this material suffered after the colonization by plants. We had a lot of soil forming processes that were triggered, such as bioturbation, iron reduction or glaciation, translocation of iron forms, and reprecipitation of those iron forms. So soil forming processes that we can see in natural soils were occurring very fast in this material. And this material was very fastly transformed. These iron oxides from the iron mine tailings were fastly transformed into a soil. But because of the title of my talk here today, what I would like to show you with more detail is the carbon behavior. So after this transformation from the iron mine tailings into soils, what we saw in terms of carbon was that at the beginning, soon after the mine collapsed and the material deposited in the estuarine environment, in the estuarine soils, we had an amount of carbon that was about 0.4% of organic carbon. And a few years later, 6 years later, we reached values of 2.3% of soil organic carbon. Of course, much of this carbon coming from plants and also biological activity. Bioturbation helped a lot to take those surface organic matter and transport them to deeper layers. But this increase, which was super fast in soil organic carbon, was combined not only by, of course, an increase in total organic carbon content, but we can see a gradual increase in total organic carbon, but also in a shift in crystallinity of the iron oxides. So the shorts or the iron oxides were produced by the new geochemical conditions that we found in the estuary. So that highly crystalline iron oxides coming from the iron mine tailings were gradually transformed into poorly crystalline iron oxides. And with that, which for me is the most interesting, is the last line here. With that, we had a sharp increase in mineral-associated organic matter, which we all know is the part of the organic matter that can last for thousands of years. So basically, our conceptual model for what's happening in those technosols is that the plant colonization triggers soil formation processes. Basically, one of the most important is adding carbon to the system, and with that, promoting a reductive environment, which will reduce iron oxides, the oscillation of water, which is common in every estuary environment, will produce the reprecipitation of iron oxides as poorly crystalline iron oxides, which we know are super reactive towards organic matter and have a strong affinity for interacting with organic matter in a stable way. So producing mineral-associated organic matter, or MAOM. Basically, to sum this up, our conceptual model is that the natural processes that occur in estuarine soils with over the iron mine tailings is changing the crystallinity of the iron oxides from highly crystalline iron oxides to poorly crystalline iron oxides, and then sequestering and stabilizing carbon in a very stable way through mineral organic associations. The next unintentional case that I would like to show, and then we can move to the intentionally produced technosols, is the work that was conducted by Dr. Francisco Ruiz on basically on a mine that operates through open mine pits, extracting dolomitic limestones. So what this company is used to do, and you can see in these slides, all the areas in red, they represent former open pits that were backfilled with siltstones and black shales that are actually waste for their operation. So they are used to close the open pits and then plant them. So those sites in red are actually former open pits that were closed and then planted with sugarcane with 3 years, with 7 years, and a pasture with 20 years, and a natural pasture that we used for our comparison. So this is the scenario before land reclamation. And this is the scenario, the image of the first or the youngest mine pits that was closed with the waste. And we can see in this picture, looking at the soil in the right, we can see that it shows almost nothing of changes in morphology. It has little or no sign of pedogenetic development or action of soil formation. So, but when we move to the second technosol with sugarcane, after 7 years, we can start to see changes in color. We can see changes in some production of clay material, and also some incipient aggregation, soil aggregates being formed. We did, of course, not only macro morphological analysis, but also thin section analysis, where we could see the incipient aggregates becoming to form in this technosol. But what is for me the cherry on the top is this soil. This technosol has 20 years of origin. So they backfilled the open pit with the same material and planted with pasture. And after 20 years, we have this soil, a very dark black soil, rich in carbon, with a very pronounced morphological transformation, evidencing a very fast pedogenetic development within 20 years. So when we put them side by side, the three soils, we can see that in 20 years we had a very fast pedogenesis with aggregation formation, with carbon sequestration, with genesis of clay material. And the most importantly for the talk today is the amount of carbon in this pasture soil with 20 years, where we found amounts of carbon that are over 9% of organic carbon, which for Brazil is too much. It's a lot. So it's a very rich soil in organic carbon. And we wanted, of course, and this was the Francisco PhD thesis, we wanted to delve into this soil and understand how is it possible for a technosol with 20 years constructed from waste, with no planning at all, unintentionally, can sequester this amount of carbon. So we did a lot of work and published some papers on it. So the first work was to understand of course, the pedogenesis to get to the carbon. So we studied the rhizosphere of those grasses, and we could see that in the rhizospheric environment, of course, we had a geochemical condition very prone to bioweathering, the primary minerals. From this bioweathering, we had, of course, the release, because it's a limestone of dolomitic limestone, the release a lot of calcium, magnesium, and also the formation of new minerals, new clay minerals. And those minerals were very reactive toward carbon. Those new surfaces of clay And through cation bridging, we could see and prove that there was a synergy between the weathering of those primary minerals, forming newly formed clay minerals, and then the organomineral interactions with organic carbon. So we were able to see that the mayom was much higher in the soil when compared to the other soils, including the natural soils. And also we were able to perform some analysis to see that the organic matter in mayom in this soil was biologically more stable and also thermically more stable through rock eval analysis. And of course, those newly formed clay minerals also triggered the genesis of soil aggregates. And we were able to see in this last work through thin section analysis that most of this particulate organic matter was occluded or protected inside the aggregates that were newly formed. So in only 20 years, everything, all of this happened, showing the potential of Technosols to sequester organic carbon in a very stable way. And to close up, we did work with my good friend and research partner, Mauricio Querubim. And this work, we analyzed the soil health index of these three Technosols, and we can see that over time, the Technosols showed an increase in soil quality index, demonstrating that the Technosols can have a real ability to provide soil function, but also different ecosystem services. And then to close up, we can talk about the intentional Technosols, the Technosols that we can produce by combining different solid wastes and maybe produce soils that will function healthily and provide soil functions and ecosystem services. Of course, we cannot use every waste, but we can try to mix, as Professor DeSutter showed, a mixture of materials to produce a functional soil. So I will close up with two works where we did this intentionally, but it is important to mention that every time that you do that, you produce an artificial soil or a technosol intentionally, it's super important that we first understand the biogeochemical functioning of natural soils. These natural soils are our models. So we have to understand deeply how natural soils work so we are able to produce effective technosols. So the first example for intentionally formed technosols is a work of a master student that worked with construction and demolition waste. Tayana did this work. What we did was we combined waste material from construction demolition with different granulometries, particle size, and then also other wastes that we have in our, let's say, in our portfolio. But the idea was to use the highest amount possible of construction and demolition waste. And then Tayana tried to see if these substrate, these newly formed technosols would be able to support the vegetation, the growth of two native tree species from Brazil. So in the left here, we can see the experiments. In red, we can see the natural soil, the control. And if we look at this picture, we can see that treatments 3 and 4 show technosols, plants that are growing, are showing a higher growth, a higher production of above ground biomass when compared, including to the natural soil. What is beautiful about this work is that when we move to the soil health index, the soil health index showed us exactly what the plants were showing, that Technosol 3 and 4 showed the higher plants biomass production, but also showed us the highest scores in soil health index. So it's a very nice work that shows that we can produce healthy technosols from waste. And if we consider the future scenarios where we have a prediction of intense urban growth in everywhere. And of course, it is expected that with urban growth, we are going to have more and more waste generation, including construction and demolition waste. Maybe Technosols, constructed Technosols, can be an alternative for managing those wastes, for producing healthy soils, and also contributing to restoration of degraded areas. And the last example that I would like to show is a work of for a PhD that is still working on this, Beatriz. She's working with Technosols constructed from iron mine tailings. So the idea, of course, came from that first example that I presented here. So in the right, we can see the experiment of Beatriz. So the idea is to test several Technosols formulations with different amounts of iron tailings and other wastes that we have in our portfolio, and then plants with grass to evaluate the growth of plant, but also to evaluate the capacity of those Technosols to sequester carbon efficiently. Okay, so those are the treatments that we have been using, the proportions of iron mine tailings and other materials. Beatriz was very happy we were very happy with this paper that she published recently, showing that, again, the Technosols, the different Technosols, were able to show higher above ground and root biomass when compared to a natural soil, which is an oxysol that we have here on campus, actually. So, and probably because when she did further analysis, probably this higher vegetation growth was related to a better chemical conditions in the Technosols. You can see a good separation between the control, the natural soil, and the Technosols, which showed higher calcium contents, higher phosphorus content, and higher pH. So again, those plants really loved growing in the Technosol. And now, still in preparation, Beatriz is performing a more detailed analysis on soil organic carbon. We are already seeing sharp increases in organic carbon contents in the Technosols when compared to the control soil, to the natural soil. But now we are moving to the physical fractionation and examining the specifics of the organo-mineral interaction mechanisms. This is the last work that I'm going to show of our group. So since we have been working so much with mining sites and mining cases, let's say, we used to have this question, right? Is that possible that Technosols could help Brazil to offset the CO2 emissions that would come from mining? So what we did in this work was we combined the geolocation of open mine pits in Brazil, mine sites with open mine pits, and we crossed this geolocation with carbon stocks data sets to see first the amount of area that could be used to that we could use Technosol to restore. So the amount of area is 6 million hectares. So Brazil has 6 million hectares of area of open mine pits that could be restored with Technosols. It's larger than the state of Rio de Janeiro. And the amount of CO2 that is emitted when you convert a site, a natural area, to an open mine pit is 2.5 gigatons of CO2 for the entire area of mining in Brazil. So in this work, we were able to show that if Brazil used the strategy of backfilling the open pits with Technosols constructed from waste, it could potentially offset from 30 to 6% of the soil-related CO2 emissions. So this shows that Technosols can be a very good strategy against climate change. Okay, so I think this is the main message that I wanted to pass. And just to close as a final message, I think it's important to highlight that studying Technosols, either those formed intentionally or non-intentionally, can bring us a deeper understanding on soil forming processes, on biogeochemical functioning of soils, and also can help us to reach global goals such as ecosystem restoration and climate change mitigation. I'll leave here my email, and also I would like to invite you all, take this opportunity to invite you all to come to Brazil for the 10th International Symposium of Soil Organic Matter. It will take place in the city of São Paulo between the day in May, between 25 and 29 of the next year. Thank you so much for your attention.
Thank you very much, Tiago, for this fantastic and insightful presentation. We truly appreciate your contribution with this live today. We will now move to our questions and answer session, and I kindly invite everyone to submit your questions in the chat, please. If possible, identify yourselves, indicate your institution or location, and specify which speaker is your question directed for, or let us know if it is intended for both speakers. I will remain here as the moderator for this final part of the webinar, so please feel free to send your questions at any moment. Now we have some questions already for you guys, and I will alternate one question for each of you. So let me see. Here for Tom. North Dakota has so many miles of this strip of disturbed soils. After construction, is the compaction in the surface zone of the soil greater than in the surface zone? If so, can that be remediated?
Exceptionally valid question. Again, the question revolves around where is the compaction in the profile. And most of the time with, if you look at large machinery, the compaction tends to be in the subsoil more so in the actual surface. That being said, soil crusting, which can occur due to the presence of sodium, in overabundance of sodium compared to calcium and magnesium in a soil that has low electrical conductivity, can create some, if you want to call it compaction, hard setting or crusting at the soil surface. And so most of the time, I think that 0 to 6 inches, 0 to 4 inches tends to alleviate itself a little bit better, but the subsoil compaction tends to last quite a while. Deep ripping is something that is done. They try to get down to that 20 inches. Takes a lot of horsepower to do that, and so it's not the first thing that somebody would choose, but it's definitely an option in those situations.
Excellent. Now, Tiago, after the dam collapse event, as the iron oxides on the island were transformed to a soil, how did the soil pH change over the time? Was pH change important to plant growth?
Yeah, thanks for the question. Actually, the pH remained very close to neutrality, which is very common in estuarine conditions and in soils that have some redox fluctuation. So the pH was circumneutral to all those years with some variation between seasons. But I think that what was more important for plant growth was the presence of finer material. So as I showed in one of the first images, we used to have very sandy and bare islands, fluvial islands in that estuary, that with the incoming of fine iron mine tailings, the plants were able to colonize those tailings and start transforming them. So I think it was more like a physical matter than a chemical matter for the plants to start grow. And of course, with the dam collapse, we have like we are in Brazil and know what happened. Some cities almost disappear from the map. So we had like a tsunami of material coming to the estuary. And I think that with that, many seedlings of plants maybe arrived in the estuary, also helping the colonization by plants.
Okay. Now I keep with you, Tiago, just to alternate. Okay. Technosols vary widely depending on the materials used in their construction. Based on your recent findings, which engineering components or design strategies have demonstrated the greatest potential for enhancing carbon storage while simultaneously promoting soil function recovery?
Yeah, that's a great question, and we are on it. So, yeah. So actually, what we are trying to do now, I mean, I showed the last work from Beatriz, where we just mixed iron mine tailings with other materials that we have in our portfolio to try to see if those technosols would promote plant growth. This is the first and most important thing. And then move to the carbon stabilization through organometer interactions. But I can say that we are now moving to modulating those materials. So what I mean is we can get some waste and change its properties for it to interact better with organic matter in a way that we want it to interact. So if I want to promote a cation bridging mechanism, if I want to promote a co-precipitation mechanism, we can modulate the material to have the outcome that we desire. So we have many materials that we are working with, but that's sort of the approach that we are doing when it comes to carbon sequestration and soil function recovery. Yes.
And do you already have identified which materials do not to use? Because it's important to know what to do, but not what not to do.
Yeah. That's why I try to be clear in we cannot use every waste, of course. We usually do a very thorough screening of potentially toxic elements. We usually do leaching experiments to see if there is any risk. Okay. So there are not a lot materials close to us that we can use. But yeah, we already have a good number of materials, and we can play a lot with different formulas. Yeah.
Okay, great. Tom, in water-limited environments, many reclamation strategies must balance cost, feasibility, and long-term sustainability. In your experience, which simple intervention has shown the most consistent improvement in soil function under severe moisture constraints, and what makes it particularly effective compared to more complex approaches?
Okay, yes. So the question revolves around, hey, what works, right? And which is the least expensive? And so I think one of the first things that we should always think about, especially in these water limited environments, is using the term that I didn't make it up, but it fits. It's don't farm naked. And so meaning that keep the soil covered. And so most farmers that are successful, or at least tend to that direction in these semi-arid environments, practice no tillage. And so basically keeping the residue on the soil to reduce the evaporation, right? So if we can keep water in the soil longer, we're going to get more plant growth, and we're going to get more root growth. When you get more root growth, you get more carbon in the soil. And so it kind of revolves around that, are there amendments that can help? Yes, there's, depending if it's a chemistry issue with sodium, you can add gypsum. If it's a soil that's on the lower left hand of the textural triangle, maybe we can add some super absorbent polymers. But at the end of the day, it ends up being like that quote from Les Hendry. It's basically water. And so if we can keep more water in the soil, covering or retaining, we're going to increase our reclamation success. Now, that being said, in cultivated cropland situations, those folks have an advantage because we can apply fertilizer, we can apply herbicides. But if you're in a rangeland situation, which North Dakota probably has 25 million acres of natural or rangeland, it's a little more complicated to get the reclamation to be successful. So we really rely on plants, and we really rely on adding straw mulch to the surface to reduce that evaporation after those disturbances have occurred.
Yes. Okay, still with you. When blending A and B horizon materials, how much of the success measured by crop yield of blending is related to organic matter, stabilizing the bulk density and preventing compaction, versus how much is related to the impact of water holding capacity and nutrients like nitrogen and phosphorus in the organic matter? This is something related that you were talking, that is
Right,
important to have the soil covered.
Yeah, of course. I think a lot of it has to do with the organic carbon, which then ties into that nutrient cycling. Where that cutoff is, I don't know. Is it, back when I was kind of brainstorming, is a 1-to-1 blend? Yes, we can run an ANOVA on that, but we can't run a regression to see where our tipping point is. And so that's, I think, where the organic matter's going to be more, bulk density is always going to be important, because that influences infiltration or saturated hydraulic conductivity or water retention, right? Because bulk density drives total porosity, which then drives everything else. And that's why we spend so much time and energy quantifying bulk density. But I do think the organic matter in this situation was probably what drove the yields to be very similar when we had our blends.
Tiago, in the transformation of dolomitic limestone, what kinds of clay-sized minerals were formed? Were they silicate minerals?
Yeah, actually, thanks for the question. Actually, we had, as I mentioned, in that mine, they used a black shale and a siltstone to backfill the open pits. And then they planted the sugarcane and the grass. And what we did was to analyze and investigate the clay minerals that were being formed inside in the rhizospheric soil and in the bulk soil. And what we saw in our study is that, of course, there is an inheritance from the parent materials of some, for example, elite. But most of the minerals that were being formed through transformation of elite into smectite. So we modeled the XRD through new modes, and we could see a lot of interstratified minerals moving from elite to smectite, which are super reactive and were taking part in the mineral-organic interactions.
Interesting. Tom, when modifying soil materials with kaolite or montmorillonite, was there any impact on bulk density too? Was the montmorillonite sodium saturated or calcium saturated to begin with?
Yeah, so the question is, what were the makeup of those, was it calcium montmorillonite or was it sodium montmorillonite? Which is a good question, because if you have sodium montmorillonite and you disperse or swell those clay sheets with a low electrical conductivity infiltrating solution, you're going to create basically a low hydraulic conductivity, right? And so in our case, we use calcium montmorillonite, and then our infiltrating solution was 0.01 molar calcium chloride. And so having an understanding of sodium affected soils, we wanted to make sure that we basically eliminated any swelling that occurred. So, but a valid question, because there's a lot of sodium montmorillonites that are sold that one can use. And so, yeah, very, very good question.
Okay. Tiago, in the soil derived from dolomitic limestone, what proportion of the total carbon was organic carbon?
Yeah, that figure that I showed, 9.6%, everything was organic carbon. Organic carbon. We have to deduce some carbon that came from the black shale, which has carbon. The black shale has carbon, but we use an isotopy to remove the contribution from the black shale. So 9.6% come from plants, so organic carbon. It's amazing, yeah.
That's amazing. Tom, we are moving to the final part of the questions here. Tom, what salts are produced waters made up of, and what now happens with these produced waters after they come to the surface?
Yeah, I mean, just on a daily basis, at a minimum, there's about 1.2 million barrels of salt water that comes to the surface with the oil and with the natural gas. And so the disposal of that salt water, it moves from the well pad and basically gets routed to deep injection wells. And these wells push this about 4,000 feet below the ground surface. And so that's where it is supposed to go. There are accidental releases which are not desirable by anyone. But the salt concentration is dominantly sodium chloride. And so in North Dakota, we are not a sodium chloride dominated salt state. We mostly have calcium sulfate, magnesium sulfate, and sodium sulfate. We have some, but very little chloride in our groundwaters and our parent materials. And so it's more easy to determine that it's a saltwater spill or a produced water spill because of the chloride signature or the bromide signature in those produced waters. And so that's chloride is used as the indicator for cleanup because of the fact that it's not readily found in our natural groundwaters. And so,
Tiago, when you are constructing new soils, what kinds of tillage implements have been used to prepare seed beds to plants to be established?
Yeah, that's a great question.
Yes.
Unfortunately, we didn't get to this part because we have only worked with, let's say, mesocosmos experiments. We have field experiments, but as I showed, we
Some
have
pictures.
we excavated some of the natural soil off and then put the Technosol inside porous bags. But yeah, we are excited to move to real field experiments, and then I will have this question for
Another presentation.
what implements we are going to use. Yeah, but we didn't get to this part, unfortunately, yet. But we'll get there.
Okay, last question for Tom, then I have one more for you, Tiago. Tom, are the super absorbent polymers biodegradable over time? If so, over how long a time?
right. So the question is, are these SAPs, do they degrade or do they
Yes.
just kind of hang around?
And how long?
And if they hang around, how long do they hang around? And so based on Megan's review of literature, there wasn't a lot of conclusive evidence of how long they hang around. And so that was a hole that she found, was that there wasn't good data on how long they're going to last. But most of them, I think the literature tends to show that it is biodegradable. Just, I think it would go back to if you had it in a high organic matter environment with 60% water filled pore space, most things are going to be degradable within that environment. If it's a low organic matter environment with very little water, probably the microbial activity is going to be, it will be much less. And so the half-life will probably be extended of those. The one thing that we've been wanting to do and haven't gotten a chance to really look into it yet are ones that can actually handle being in saline environments. most of the ones that we've looked at or investigated, they degrade or they don't work properly when there's salts, excess ions in the soil. And so from our salt affected soils, if we can keep more water available to the plant, we can get plants to, as long as the ions aren't toxic, we can get them to grow a little bit more longer in a higher saline environment. So I think that's a really good avenue for new research, is some of these super absorbent polymers that can handle greater ionic strength, basically. So.
Okay. For Tiago, what do you see as the next steps for advancing Technosols research, especially their applications for combating and mitigating climate change?
Yeah, so I think that our next steps would be actually advancing on how to modulate those materials. I mean, screening is very important, finding materials that have potential, but I think the challenge is how to modulate them, how to alter their conditions, how to boost a good condition to be better, yet better, and to foster the exact mechanisms that we are aiming for in terms of organic matter interactions. Yeah. So modulating them before using is, I think, the next step, and then move again to the field trials with plants and see how they behave. Yeah.
I have a question from Professor Lucia Anjos for both of you. Congratulations to the speakers, Society of Brazil and Society of America. How to insert importance of this research with Technosols in policies and plans for restoration in contaminated areas? Tom?
Good question. Yeah, good question.
Yeah. For both of you.
Yeah, I think our societies are well tuned for the inclusion of anything that's related to disturbed soils or salinity, sordicity, acidic problems, soils, acid mine drainage, and so it's just a matter of somebody creating a division or being a leader in that division or in that community, if it's ASA, and kind of just running with it. And so certainly we would, I think I will speak for my partner here, we'd be overwhelmed if there was more of a presence in our societies with that. And I will say the professional soil scientists, the people who are doing this on a day-to-day basis, I think they would love to have this type of conversation within our societies as well, because they're the ones out there trying everything all the time, every day. And so I think we could do better by helping them as well.
Right. Evan?
Yeah, I agree. I think that for starters, we have to be able to publicize more, not only on scientific papers, but to show the potential of Technosols to not only reclaim degraded areas, but also recover contaminated areas. I didn't have the time to show, but we did some work with contaminated wastewater using Technosols to act as a trap, a geochemical trap to contaminants. So I think it is important in Brazil, more people to work with Technosols. And I think that, for my point of view, understanding the mechanisms is super important for these Technosols to behave adequately. I mean, it's not mixing materials by chance. It is understanding the processes and trying to mimic them and force them. So I think we need more research in Brazil in Technosols. We have very few works done in it, and publicize this to policymakers, to governments, so this type of solution can reach the levels that we need to reach. Yeah.
Show them that we do science for them. for people.
Exactly.
Okay. Well, thank you. We had great questions and even more better answers from you guys. Thanks for your time. And the time is coming to an end. So I would like to thank you again for your questions and the people who sent the questions and for the rich discussions. It was more like an extension of your presentation with those questions here and your answers as well. And it is my pleasure now to turn the floor to Dr. John Kovar again, who will offer his concluding remarks on behalf of the Soil Science Society of America. John, the floor is yours.
Well, thank you. Yes, thanks to both of you gentlemen for your presentations. Excellent. I'm sure we could go on for a while longer with questions and comments here, so it could turn into quite a discussion. But unfortunately, our time is ending for today. And so I thank you, our speakers, and all of our participants. And I have no idea how many people participated in this webinar, but hopefully quite a few. We will continue this, and we look for more collaborative events as the days go on. So our committee will meet next year, and we'll continue our work. I would like, as a final reminder, that World Soil Day is December 5th. And so I looked online, and there's a lot of information online if you just type in World Soil Day 2025. So yeah, do that and you'll find good information. One of the sites that I came to, their theme was soils where food begins. And I thought that's a good theme. So with that, thanks to everyone, and we'll see you next time.